Hi, my name is Edward, and in this part of the project, I'll be discussing the biophysical characteristics of the neural cell, mainly in regards to the action potential. So, to begin with, movement in the body, like muscle contractions, are aided by the neuron cell, which creates and communicates electrical signals to the body. The signals are created by the displacement of charged ions across the neuron's cell membrane, causing a difference in voltage. These difference in electrical potential is how the neuron cell communicates with the body. So with a brief overview, imagine like when your body's at rest, the inside of the neuron cell membrane is negatively charged and the outside is filled with positively charged ions. This difference creates an electrical potential across the membrane. When the body feels something external that causes a reaction like touching a hot object, the neuron activates its action potential, moving Na plus and K plus ions across its membrane through a voltage gated channels that is respective of the ions. And physically, with Coulomb's law, where opposite charges attract, this is effectively seen in the behavior of the neuron cell. Before any movements or stimulations of the body, the cell membrane of the neuron has a resting potential of minus 70 millivolts, which is maintained by its sodium and potassium channels. Later in the video, we will do an example problem that talks about the work done by the pump or like the channels to maintain the resting potential. When an external stimuli occurs, the voltage of the membrane approaches its minus 55 millivolts threshold. When the threshold is reached, Na plus ions rush into the membrane through the sodium channel, positively increasing the voltage of the cell membrane. This process is called depolarization. Physically, the movement of Na plus ions creates electrical potential difference, therefore doing work to move across the membrane from a high concentration state to a lower concentration state. So in order for the neuron cell to fire neurons again, it needs to be restored back to its resting potential. The repolarization process aids in restoring the inside of the membrane back to its negative voltage. The repolarization process is where sodium channel closes and potassium channel opens, allowing K plus ions to move out of the membrane. The efflux of K plus ions helps the membrane to return back to its negative internal charge. In an attempt to restore the neuron cell back to its resting potential voltage during repolarization, the efflux of K plus ions sometimes exits the cell much more than need be because the potassium channel stays open a bit longer, allowing more K plus ions to leave the cell membrane, causing it to be more negatively charged to a voltage of about minus 80 millivolts. The hyperpolarization process ensures that the neuron membrane is restored back to its resting potential voltage of minus 70 millivolts. For this to take place, sodium potassium channel open, allowing K plus ions and Na plus ions to move into the cell membrane to balance out the excessive negative charge, therefore restoring the resting potential. Finally, some applications of um, action potentials are seen in therapy. For example, in cardiac pacemakers, deep brain stimulation, and uh, FES, functional electrical stimulation. These processes help, stimulate body movements, muscle contraction to help the process of like healing or restoring any dead cells in the body.
For this question, we're going to go through a biophysics problem. We're going to calculate the Gibbs free energy and work required to move some sodium across this membrane. For this problem, we have a few assumptions. We're going to say the concentrations are constant throughout this problem, which are listed here. We're going to say there's no interactions between these molecules, and there's a constant electrical field drop across this membrane. We're also ignoring chlorine ions in this problem. And so in our visualize, we can see there's a sodium-potassium pump, ATPase, moving sodium ions and potassium ions across the membrane. For our unknowns, we're given that the concentrations in millimoles, the permeability of sodium, and also the concentrations of potassium and the permeability. We're also given the temperature of the body, which is roughly 310 Kelvin, and what we're solving for is the Gibbs free energy and work required to transport sodium across this potential difference. All right, the first step to solving this problem is to calculate the voltage of the membrane. And to do that, we're going to use the GHK equation, which says that R times T. R is the ideal gas constant, T is the temperature, over F, which is Faraday's constant, times the natural log of the permeability of K, times the concentration of K on the outside, plus the permeability of sodium times the concentration of sodium in the outside over the permeability of calcium on the inside plus the permeability of sodium on the inside is equal to the membrane potential. And if we plug in our values, we get negative 68.6 millivolts. And we can check the units real quick. R is in joules per mole Kelvin. T is in temperature. Faraday's constant is in coulombs per mole. And as we can see, moles cancel, kelvins cancel, and we're left with joules per coulomb, which is a volt. And I converted it to millivolts. All right, so now since we calculated the membrane potential, we're going to use that to calculate delta G. Delta G is known as Gibbs free energy. It's a thermodynamics property. It's related to work. It's the maximum amount of work that can be done. And we're just going to talk a little bit about what this equation means. Delta G standard is the Gibbs free energy under standard conditions, which in this case would be if the concentrations were 1 molar, but they're not. So this is what is compensating for that fact. And to calculate delta G standard, we can use an electrochemical equation, which says delta G standard equals negative N F delta E cell. Negative N is the number of electrons that are being transferred, or the charge transferred per ion. F is Faraday's constant, as we used earlier. Delta E cell is the membrane potential that we calculated. And we're familiar with delta E cell or delta E. We've used it in multiple applications like mass spectrometry. The second part, RTL and Q. Q is the reaction quotient. It just tells us Q, to calculate Q, is just the products over the reactants. And in our case, since the sodium ions are going outside, these are our products, these are our reactants. And so we can see from this equation there are two properties governing delta G. One is the concentrations and electrical potential. This one makes sense. You're moving something from lower concentration to higher concentration. This is an example of active transport, which requires energy. All right, so now we just plug in our values into this equation. N is the charge of the sodium ion, which is 1. This is Faraday's constant. This is the membrane potential, which we calculated up here. R is the ideal gas constant. This is the temperature. And then Q, which is the concentration of sodium outside over the concentration inside. And that gets us 12.5 kilojoules per mole. And quick unit check, we can see that the coulomb times a volt is just the joule. So this is joules per mole. Then the temperature, the kelvins cancel, the millimoles cancel. So we're left with joules per mole times 10 to the negative third gives you kilojoules. And from this positive value of delta G, we know it's not spontaneous, which makes sense since you're moving from lower concentration to higher concentration. And this is also equivalent to the work done per mole. And so where is this energy coming from when you're trying to move the sodium ion across? It comes from the hydrolysis of ATP. So this sodium potassium ATPase pump, the sodium potassium pump, it hydrolyzes ATP, and whenever a ATP is hydrolyzed, 3 sodium ions come in, and then 3 potassium ions go out. And if we want to calculate the work done per ion, we just need to take the work done for a mole and divide that by Avogadro's number, which gets you 2.07 times 10 to the negative 20 joules per atom.